very good morning to all. I'm Dr. Shugufta Khan from School of Electrical, Electronics and Communication Engineering. So today we will discuss about the HVDC projects in India. So this topic comes under the subject facts in HVDC. Transmission network at present what we have the voltage level that is 765 kV, 400 kV, 220 kV transmission lines we have. Then HVDC back-to-back combination is there. Then total 22 fixed switched capacitors are already installed in AC transmission system. Then there is a control series capacitor TCSC. 6 TCSCs are installed in case of the AC transmission system. So at present we have 5 national grids, that is the northern region, then northeastern region grid, and then the eastern region and the southern region and the western region. So all 5 grids are interconnected. Now the energy resources map. Energy resources like coal, water, etc. are unevenly distributed within the India. So coal centers we can have in India, that like Chhattisgarh, Odisha, Jharkhand, then Madhya Pradesh, and in case of the hydro, the northeastern and the northern Himalayan region basically are the sources of the hydro energy. Then coastal based we are having that Andhra Pradesh, Tamil Nadu and Gujarat. So the different energy sources are distributed in India at different places. Increase in transmission voltage, as we know the power, if we transmit high voltages the losses will be less. You know the formula of the losses, ohmic losses, that is I square into R, and for the same power flow the current expression we can write I is equal to P upon V. So we can say the current is inversely proportional to the voltage. So if the voltage is high the current will also be less. So the total ohmic losses, that is I square R, will be less. So high voltage is always in demand in case of the transmission system to reduce the ohmic losses. So in 1977, that time 400 kV voltage was the level for the transmission. Then 1919, then again 500 kV was available for that transmission. Then in 2000, that is 765 kV was introduced. Then HVDC in 2012, 800 kV HVDC voltage level was developed, and next to planning it is a 1200 kV voltage. So that's why the voltage is increasing to transmit the power in a transmission line. 500 kV 1500 megawatt Rihan Dadri HVDC project. So in this project, and that is plus minus 500 kV, so bipole HVDC system, and then power rating is 1500 megawatt. Total number of poles are 2. Then because it's plus minus rating is given, so bipole system. Then AC voltage is 400 kV, and the DC voltage that is plus minus 500 kV, and the converter transformer at the Rihan terminal, and it is 6 into 315 MVA. So that means we are having 6 converters which are having each unit is of 315 MVA. Then Dadri terminal is also having the 6, and each unit is producing 305 MVA. Total length over overhead transmission line in this project, that is 816 kilometer. So this is the actually first project in India. So plus minus 500 kV 1500 megawatt HVDC bipolar transmission link will supply the bulk power from thermal power plant of Rihand to Dadri, that is the western part of northern grid, and the Rihand is in the eastern part of the northern grid. So this power is transmitting from grid to grid, and then each pole constitute power carrying capacity, that is 750 megawatt with 10% 2 hours overload and 33% 5-second overloading capability. And the reserve power flow capability is also available in this project. Then during inclement weather condition, power transmission possible at plus minus 500 kV DC voltage also. So this is also the provision in this project. Now the 2 into 250 megawatt HVDC Vindhyachal back-to-back station. So here both the rectifier inverter both are available at the same location. So here power rating is 2 into 250 megawatt. Two units are used. Then number of blocks are 2. DC AC voltage 400 kV and the DC voltage is plus minus 70 kV. And the converter transformer is of the rating 8 into 156 MVA. Now the salient features of this project, that is it connects Vindhyachal Super Thermal Power Station Western region to Singrauli Super Thermal Power Station Northern region in Indian grid. Each block power carrying capacity is 250 megawatt and it's a bidirectional power flow capability is also available in this project. The project achieved load diversity of northern and western region in Indian grid by meeting high demand from surplus power available in either region. And then first commercial back-to-back HVDC station in India, that is the first commercial HVDC back-to-back station which was installed in Vindhyachal. 2 into 500 megawatt HVDC Chandrapur back-to-back station. So here the start date was 1993 November. It was started. Then completion date and December 1997. Approximately 4 years taken in this project. Then power rating is 2 into 500 megawatt. Then number of blocks 2 and the AC voltage 400. DC voltage is 205 kilovolt. Then the converter transformer 12 into 234 MVA rating. Now see this the features of this project. It connects Chandrapur thermal power station western region to the southern region thermal power station in India grid. Each block power carrying is 500 megawatt and bidirectional power flow capability is also available. Project achieved load diversity of western and southern region in India grid by meeting high demand from surplus power available in either region. Then second for commercial back-to-back HVDC station, that is called now the plus minus 500 kV 2000 megawatt HVDC Talcher Kolar station, and this was completed in June 2003. Then the main data is like power rating 2000 megawatt, power rating increased to 2000 megawatt. The number of poles 2, AC voltage 400 kV and DC voltage is plus minus 500 kV. Converter transformer Talcher, that is whatever the converter transformer is used at the Talcher station, that is 6 into 398 MVA rating. And the Kolar is at the Kolar station this transformer rating is 6 into 398 MVA. So length of overhead DC transmission line is 1369 kilometer and this is the longest commercial HVDC link in India. Now the upgradation of till now we were having the plus minus 500 kV HVDC system. Now there is upgradation of plus minus 500 kV HVDC Talcher Kolar link from 2000 megawatt to 25,000 megawatt. Same actually project in the same project there was the power was increased from 2000 megawatt to 2500 megawatt. So HVDC Talcher Kolar link was designed for 2000 megawatt continuous rating with inherent short-term overload capacity depending on the ambient temperature, then prevailing voltage at Talcher and Kolar and cooling mechanism. Further, DC bipole lines with quad conductor was capable to transmit 1250 megawatt continuously with marginal incremental loss. So the inherent overload capability was utilized to meet the system so that this facility was available. So that's why it was used and it is upgraded to 2500 megawatt from 2000 megawatt. This enhanced capacity is to be used only under contingency condition. So HVDC capacity for them it is increased to 2500 megawatt in case of the contingency or any emergency condition. Now the 1 into 5,500 megawatt HVDC Sasaram back-to-back station in Bihar. This station was completed. This project was completed in September 2002. Then power rating is 1 into 500 megawatt. Number of blocks were used in this, that is 1. And AC voltage is 400 kV. DC voltage it is 205 kV. Converter transformer 6 into 235 MVA rating. The connects so the eastern region to Sasaram, eastern part of the northern region. Indian grid power transfer mainly from eastern region to northern region. Now the 2 into 500 megawatt HVDC back-to-back station at Gajuwaka. So completion date was in Feb 1999. It's two blocks are there. So block 2 is completed in March 2005, and the main data of that project. Equipments, so the power rating is 2 into 500 megawatt, and the number of blocks are 2. AC voltage is 400 kV, then DC voltage is 205 kV for the block 1, as two blocks are there. So for block 1 the 205 kV voltage level, then 177 kV for block number 2. And the converter transformer for the block 1, it's the rating of 6 into 234 MVA, and for block 2 its rating is 6 into 201.2 MVA. Now the 2 into 500 megawatt HVDC station, so that what was the salient features? Salient features, it connects Jaipur eastern region to Gajuwaka southern region. Thermal power station of Indian grid. Each block power carrying capacity is 500 megawatt, and the bidirectional power flow capability is also available. We can transmit power from the southern region to the eastern region also. So the project achieved load diversity of eastern and southern region and grid by meeting high demand from surplus power available. Now see the Balia-Bhiwadi transmission line project. It is working on plus minus 500 kV, 2500 megawatt. So and power rating, it was commissioned in on 31st of March 2010. Then power rating is 2500 megawatt, and number of poles are used, two to bipole system is used. Then AC voltage is 400 kV, DC voltage is plus minus 500 kV. So mostly we use the bipole type of the configuration of HVDC. The length of overhead DC line is 780 kilometer, and converter transformer at Balia, it is the rating 8 into 498 MVA, and the converter transformer at Bhiwadi station, that is 8 into 498 MVA rating. Now the features of this project, that is bipole plus minus 500 kV, 2500 megawatt HVDC, and the transmission line length is 780 kilometer. It is from Balia to Bhiwadi. So Balia is in eastern part of the India and Bhiwadi is in the northern part of the India. Now the each pole power carrying capacity is 1250 megawatt, and the during unfavorable weather condition operation at 70% to 80%, and DC voltage is possible. So that is the maximum voltage we can have at the DC side. So reverse power flow capability is also there. We can actually transmit the power from Bhiwadi to Balia also. So reverse power transfer capability is possible in this project. Next, switchable configuration of a sparse converter transformer. So what are the configuration? The arrangement of a sparse converters transformer for quick restoration of pole in case of failure of converter transformer. So this facility is available in this project, and each pole is having a dedicated spare converter transformer with switching arrangement. So at the time of the emergency or any fault in that transformer, so that facility spare transfer converter transformer is also available. We can use that. Then transformer configuration being used for the first time. It is this configuration of the transformer we are using. It was used first time in this project. Next, these are the references which you can follow for this topic. Thank you so much. If you have any query related with this topic, you can ask me.